Okay, so let's review what we know about acids and bases before we move on and apply them to titrations. So acids, if you remember, I'm going to think of H+. And bases, I'm going to think of OH-. So remember we talked about H, hydrogen. When hydrogen is an atom with an atomic number of 1, that means it has 1 proton and 1 electron. So let's put that down here. H, or hydrogen, has 1 proton with a +1 charge and 1 electron with a -1 charge. How does an atom become a cation? It's going to lose an electron. So whenever he loses electron, now he's going to have 0 electrons to become H+. So let's review that. His mass is 1. That means that he has 1 proton that makes up most of his mass. He has 0 neutrons and 0 electrons. So an acid is really going to be referred to just as a proton. So acids are proton donors. That's all he is. He cannot be an electron donor because he doesn't have any electrons. So H+ has no electrons, so that means he is electron acceptor. Remember, acids and bases are opposites, so all you have to do is come up with one of these pieces, and all the rest of them will fall into place. So if an acid is a proton donor, a base must be a proton acceptor. If an acid is an electron acceptor, a base must be an electron donor. And now all of a sudden you have all 3 of our definitions of an acid. So Arrhenius states that acids provide H+ in solution and bases provide OH- in solution. Bronsted-Lowry says that acids are proton donors and bases are proton acceptors. And the Lewis definition is that an acid is an electron acceptor and a base is an electron donor. So remember we said acids have no electron here. So H+ has no electron, so he is electron poor. When you think of electron poor, we're going to think of cations with a plus charge. Bases with their OH- are electron rich. So you're going to think of anions, and bases are going to be our negatives. Now let's go to our summary of a weak acid, then a weak base reaction. Remember the general form of an acid-base reaction? HA is going to represent a weak acid, and we're going to put it in water. Acids are proton donors. Acids are H+ donors, so we're going to end up with A- and H3O+. Let me do this again so I'm not running into my base space. Got myself a little bit too big there right off the bat. Remember, the double arrow is going to tell us that this is an equilibrium. So the K expression for an acid is going to ignore the water because we only include the aqueous in these expressions. So let's do an ice chart. The general form of an ice chart is always going to be, you'll have some initial concentration of your weak acid. Water, we're going to put lines through because it's a liquid. It's not part of a K expression. And the initial for these types of problems are going to be 0 because this is before any dissociation occurs. So then this is going to be minus X, and these are going to be plus X. So this is initial concentration minus X, and these are both X. So my Ka, or acid dissociation constant, is going to be brackets for the concentration of products over reactants. So the general form will be X for A minus, X for H3O plus, so X squared on the top, and initial concentration minus X on the bottom. That is our general form. So let's remember, in order to calculate the pH, pH is going to be the negative log of the concentration of H plus. Concentration of H plus or H3O plus is the same thing. Remember, that's what X is in this particular case. So it's going to be negative log of X. So now we figured out how to solve for our Ka. We figured out how to solve for our pH. The concentration of H plus in this case is always going to be X. And then let's do our percent dissociation. Remember, our percent dissociation and our 5% rule are calculated the same way. That's going to be which part dissolves, or X, over the initial concentration, and we'll turn it into a percent by multiplying by 100. Let's go over to the base. The general form of the base is we're going to have to act like a base, and we'll put it in water. And a base is going to act like a proton acceptor. So the base on the other side is going to be, what do I look like after I've taken the H and a plus sign? And after water loses an H and a plus sign, we get a hydroxide ion, which is what we think of with bases. The general form of our ice chart. This is going to be the initial concentration minus X. We don't concern ourselves with water because it's a liquid and we're only concerned with aqueous. These start off at 0 plus X, and the general form of our ice chart will always be the same. In this case, Kb is going to be the concentration of my products over the concentration of my reactants. Ignoring water, so it's X squared over initial concentration minus X. This time we're dealing with X as representing the hydroxide concentration. So if I take the negative log of X, that's going to give me the POH. And the percent dissociation again is going to be X over the initial concentration times 100. I'm going to add underneath here. Let's draw a line. The things that are going to connect these two concepts, the acid-base concepts, the things that are going to connect these two concepts that apply to both of them are going to be pH plus POH equals 14. And then the concentration of H plus or H3O plus and the concentration of OH minus are going to equal 1 times 10 to the minus 14, which is Kw, which is also the same as Ka times Kb. Remember, our caveat is that this is all talking about at 25 degrees Celsius. Fortunately, on the AP exam, they're not going to ask you things about other temperatures. They might ask you a question about, do you know that at other temperatures, the Kw is going to be different? So let's summarize how we would know if we're dealing with an acid or a base. Acids have pHs that are less than 7. Neutral has a pH equal to 7 as long as we're at 25 degrees Celsius. Bases have a pH greater than 7. Acids have a Ka that is greater than 1 times 10 to the minus 7. And bases have a Kb that's greater than 1 times 10 to the minus 7. The Kb on an acid, which we can calculate, is going to be less than 1 times 10 to the minus 7. Like such. So here's how we can identify whether we're dealing with an acid or a base. So you also can have a POH of an acid. The POH of an acid is going to mean, okay, so it's got to be greater than 7. POH is less than 7. And that is our summary of the weak acid-base equilibria that we learned so far, and we will come back together and learn how this relates to titrations. Of course, now I had to